Hello everyone. So today we'll be discussing one more problem on Brayton cycle. Okay. So in this problem, what is the differences in the previous all problem we have solved? He has clearly mentioned what is the temperature at the inlet, that is the minimum temperature in the cycle, as well as what is the maximum temperature in the cycle. Uh, in some of the problems which are given in your examinations, what he will do is he will not give the what is the maximum temperature in the cycle. So this particular problem will fall in this particular category. See, apart from that, he will be giving other data so that you can find T3. So that is the only difference when you compare previous all problem with this particular problem. So in this problem, we shall see in an open cycle gas turbine plant, air enters the compressor at 1 bar and 27 degrees Celsius. So he has given the values related to state 1. The pressure after the compression is 4 bar. So the pressure after compression is 4 bar, though therefore your pressure ratio P2 by P1 will be equal to 4. The isentropic efficiency of turbine and compressors are given. See, isentropic efficiency of a compressor as well as a turbine is given. So therefore you have to note it down the value of 2 dash and as well as 4 dash since the efficiencies of compressor and the turbines are given. Air to fuel ratio is 80:1. This is very important. Mass flow rate of air divided by mass flow rate of fuel, he has given it as 80, and we shall see how it will be useful for the calculation. Calorific value of the fuel he has given, that is 42,000 kilojoules per kg. Mass flow rate of air he has given, that is MA here, 2.5 kgs per second. Determine the power output from the plant and the thermal efficiency. See, he has mentioned the thermal efficiency. Assume that the Cp and gamma to be same for both air and products of combustion. Products of combustion in the sense at the outlet you will be getting the gases, is it? The combustive products plus air. So even it is here saying that the values of gamma and Cp are both same for air as well as the products of combustion. You can take both the things as the same values. So let us go into the problem now. So what we have to find is the power output, which is W net, that is WT plus WC. The thermal efficiency of a Brayton cycle is given by output by input. Output is W net divided by input is heat supplied. Now this is very interesting now. The compressive output is given by MCP delta T, as you all know. Delta T being initial minus final, so it is T1 minus T2 dash here. T1 minus T2 dash. Since efficiency is given, T2 dash. Now, the turbine work output, how it is given? MCP T3 minus T4 dash. Why dash? Because efficiency of the turbine is given, so it is T3 minus T4 dash. So that is all fine, but this is very interesting. So compressor, what is a working fluid in a compressor? So in compressor only air enters, is it? Air will be compressed up till 2. From 2 you'll be adding fuel. So fuel gets burned. So mass of air plus mass of gas what are you adding will come and reach up to state 3. That means turbine is playing with both air and gases, whereas the compressor is playing with only air. So while considering MCP delta T for compressor, you have to consider it as MA, only mass of air, since compressor is dealing with only air here. While coming to the while coming to the turbine is dealing with both air as well as the combustive products, which is gases. So you have to take MA plus Mg for the turbine. So that is which is stated here. So work done by the compressor is given by M to the suffix A, that is only mass of air into Cp into delta T, T1 minus T2 dash, and the turbine work output is mass of air plus mass of fuel into Cp into T3 minus T4 dash. This is the change you have to keep in mind. Let us continue further. We shall calculate the compressive work first. So the compressive work as stated above given as MA Cp T1 minus T2 dash. MA mass flow rate of air is given in the problem. Cp you know 1.005 kilojoules per kg Kelvin. T1 is given the temperature, the initial state starting of the compression has been given, but T2 dash you don't know. So in order to find T2 dash, what we'll be using? You'll be using PVT conversion equation from process 1 to 2, which is adiabatic compression. So P1 by P2 is equals to V2 by V1 whole to the power of gamma, that is equal to T1 by T2 whole to the power of gamma divided by gamma minus 1. P2 by P1 is beta, so it is 1 by beta, that is equal to T1 by T2 whole to the power of gamma divided by gamma minus 1. Substitute the things, you know the value of beta, you know what is T1, you know what is gamma 1.4. Substitute the thing. So only T2 is unknown. So T2 is calculated as 446 Kelvin, but you require T2 dash here. How will you get T2 dash from T2? Applying the efficiency of compressor definition. What does efficiency of compressor state? Isentropic work divided by actual work. What is isentropic work? Ideal work where no dash is involved. So it is T1 minus T2. Actual work is where the dash is involved, so it is T1 minus T2 dash. So it is 0.8, it has been given. T1 you know 300, T2 you have calculated 446, T2 dash is the only unknown in this equation. So T2 dash is calculated as 482.5 Kelvin. Okay, since you have calculated T2 dash, you can easily calculate what is compressive work. So compressive work is, when you calculate the things, it will be minus 458.53 kilowatts. Always be careful about the units. So since mass flow rate of air is kgs per second, Cp is kilojoules per kg Kelvin, and your temperature is in Kelvin. What happens? Kelvin goes away. Okay, and your kg goes away, kilojoules per second remaining. So joules per second is watt, so kilowatt. So the unit would be kilowatts. Similarly, now we will go for the turbine work. So turbine work is given as the turbine is dealing with fuel as well as the air. So mass of air plus mass of fuel into Cp into T3 minus T4 dash. See, you know mass of air, mass flow rate of air, you know Cp, but you don't know what is mass flow rate of fuel, what is T3 and what is T4 dash. We'll be calculating one by one now. For the calculation of mass flow rate of fuel, the air to fuel ratio is given as 80, is it? Mass flow rate of air divided by mass flow rate of fuel is given as 80. You know what is mass flow rate of air? Okay, so by that, substituting here, what you can calculate, you can easily calculate what is mass flow rate of fuel, is it? So mass flow rate of fuel is nothing but 2.5 divided by 80. So mass flow rate of fuel is given by 0.03125 kgs per second. So first thing is been calculated, first unknown is calculated. What else we want? We want T3. So for T3, have to follow the standard procedure to calculate T3. Now, at the state 3, whatever heat is supplied by the fuel is equals to heat taken by the gases, is it? So whatever you supply, that has to be taken by the gases. How will you calculate what is the heat supplied to the fuel? Same general formula, mass flow rate of fuel into Cv. So mass flow rate of fuel into Cv will give you the amount of heat supplied by the fuel. Now, how will you calculate the heat taken by the gases? mCp delta T. What is m here? Mass of air plus mass of fuel into Cp into T3 minus T2 dash. See, this particular thing is heat calculation. For heat calculation, it would be final minus initial. So coming back to this diagram, what is final here? So final is T3 and initial is T2 dash. Clear? For the whatever the heat is taken out during the process 2 to 3, how you are calculating it? You are calculating it by mCp T3 minus T2 dash. So final minus initial for heat and initial minus final for work. Very good. This is the thing. Okay, so it is T3 minus T2 dash, final minus initial. So substitute all the things. You know mass flow rate of fuel, just calculated. Cv is given, mass flow rate of air, mass flow rate of fuel, you know, just substitute it. Cp is substitute, T3 is unknown, just keep it as it is. T2 dash you already calculated, substitute it. So in this particular equation, only T3 is unknown. If you calculate it, it comes around 992.3 Kelvin. So once the T3 is known, you know how to calculate T3 dash. You want not T3, you want T4, right? Okay, fine. So once T3 is known, you can use the PVT conversion equation for the process 3 to 4, which is adiabatic expansion. So when you use the PVT conversion equation from this, you can calculate what is T4. Once the T4 is known from the PVT conversion equation, you can use the efficiency of the turbine formula which states actual work divided by isentropic work. Actual is the thing where dash is involved, so T3 minus T4 dash. Isentropic work is nothing but which is ideal where no dashes are involved. It is just T3 and T4. You have calculated T4 from here. You know the value of T3 from here. Substitute everything. Only T4 dash would be unknown. So T4 dash you can calculate easily as 716.22 Kelvin. So once you have known T3, once you have known T4 dash and all the unknown parameters, you can easily calculate what is work done by the turbine. So work done by the turbine is given by MA plus MF into CP into T3 minus T4 dash. Substitute all the things, you'll get around 702.32 kilowatts. What is net work output? Turbine work plus compressive work, is it? So turbine work is given so and so, and compressive work is this much. So when you simplify it, when you calculate it, you'll get around 243.75 or 79 kilowatts, which is net work output. Now, but thermal efficiency is given by output by input. What is input? Heat supplied. Heat supplied is mass flow rate of fuel into CV. So it is 0.03125 into 42,000. This is the value of the heat supplied by the fuel. Okay. Uh, you can substitute directly here. What is QS? You know W net you have calculated from here. So W net divided by QS, which is this particular thing. If you substitute it, you'll get around 18.58, which is the answer for this particular question. Okay, similarly, you can try this particular thing. There was a little bit of, you might be confused when you're reading this. Therefore, I have provided a hint here. You can watch this. Okay, by this you can try this particular problem which has been asked in July 2013. After trying this, you can even try this particular problem which has been asked in December 2012 for 10 marks. So complete these two problems. Try these two problems. If you find any doubt, contact me. Okay. Have a nice day. Bye.